Greetings of the day, students. Today we will discuss about the concept of interconnection networks and decomposition techniques, which are very important with respect to parallel algorithms. So interconnection network. So where we are getting the concept of the interconnection network, when we are dividing a complex task, okay, that complex given problem and divided into tasks, these tasks are given to a processor, okay. So when there are n number of tasks that are assigned to n number of processor, when these processors are going to run, there should be a communication among these processors, okay. So that's why we are going to deal with the concept of interconnection network. That means in a network, the nodes of the processors are being kept. When certain sort of task is being assigned to these processor, during their execution they need certain sort of communication, okay. So that is the interconnection network could be classified into two types, static and dynamic. So when we talk about the static, that consists of point to point communication, okay, link among the processing nodes. This is also referred as a direct network. In dynamic network, what do we observe? The connection among the nodes are going to be carried out with switches. So this is a label diagram where we observe two kinds of network, static network and that is a dynamic network. Static network we can call that one as a direct network, and dynamic network we can call that one as a indirect network. Why we are calling the static network as a direct network? Because there is a direct communication among or connection among the various processors which are kept in the network, okay. Whereas in the why we are calling the dynamic network as an indirect network? Because here the nodes, the processor are connected with switches. So what do we observe? There is no direct connection from one switch to another switch, okay. A switch could be connected to any other switch, okay. There is no kind of order that is being followed there. So we could divide the interconnection network into static and dynamic. Static networks are assembled as direct networks, and dynamic networks are assembled as indirect network. So how we are getting direct and indirect means it depends on the direct or indirect connection among the nodes or the processor which are present in the network. So depending on that, we are having various kinds of interconnection network, okay. The first and the foremost simple one are nothing but the linear and ring interconnection. See how we are going to name them, the kind of the representation or the depending on the kind of the connection among the processor, we are going to represent them, okay. So for suppose we want to talk about a ring interconnection, okay, or linear interconnection. So here what do we observe? That is a one dimensional mesh, okay, where we could find processors that are being connected in a linear fashion. If we observe in the diagram, there are processor P0, P1, P2, P3, P4, P5. They are connected in a linear approach, okay. Next, in another approach, what do we find? Or how we can term a interconnection network as a ring? If there is a connection between the initial processor to the final processor. In the diagram, if we observe, what is the initial processor for suppose P0, and what is the final processor P5? If there is an interconnection among them, the kind of interconnection network that we are getting is nothing but a ring interconnection. So okay, depending on the kind of the arrangement of the processor and the connection among them, we could easily identify whether what kind of network we are dealing, okay. So this resembles a linear and this resembles a ring interconnection. So another interconnection, that is nothing but a shuffle. So we have to understand the interconnection network. Why we are calling this kind of interconnection network as a shuffle? Okay, because this consider here there are 8 processors starting from P0, P1, P2, P3, P4, P5 and P8. So here in which shuffle connections are illustrated by solid lines, and exchange links are represented by the solid shuffle connections. The connections here we observe in the diagram two kinds of things, arrow and line, okay, exchange links, arrow and exchange links, okay. The one that are represented with the arrow are nothing but the shuffle. That means we can shuffle the data with respect to the particular processor, and we could carry out the exchange of the data with that link, okay. So shuffling could be carried out with respect to the arrow, and exchange of the data could be carried out with respect to the links, okay, the links, okay. So that is the difference. If we observe another kind of diagram is there, we could call that one as unshuffled. Why we are calling that one as unshuffled? Because they are bidirectional. Okay, if the direction of the link is reverse, so before if you observe that means only with respect to one particular direction we could carry out the shuffling. If it is being reverse, okay, observe the same thing in the below diagram. There are bidirectional arrows that indicates unshuffled interconnections. Okay, if you are going to approach this kind of thing, okay, bidirectional arrows. Next, two dimensional mesh. Number of processors are there, and these processors are being connected with certain linear fashion. Okay, we could call them as a two dimensional mesh. Okay, the mesh topology can be generalized at two dimensional. Okay, suppose here in a q dimensional mesh, we are not mentioning that means that is one dimension or two dimension. Q dimensional mesh, each processor is connected to two neighbors, okay, in each dimension. So if we consider this one as a processor, so to how many processor it is connected, or how many neighbors it is having? Two. Towards okay, one direction we are having one processor, towards another direction we are having another processor. You consider any processor, okay, it is having certain sort of neighboring processors. Okay, so this kind of representation is nothing but called as a two dimensional mesh. Okay, next, hypercube. So hypercube, we could consider n number of processors starting from P0, P1 to Pn. Okay, and here what do we find? N is nothing but the power of 2. Okay, n equal to 2q. So q should be always greater than or equal to 0. Suppose n equal to 2 power 0. So that means we are dealing with 2 processor. Yeah, suppose q equal to 2. So we are dealing with that means 4 number of processor. N is equal to q equal to 3. We are dealing with 8 number of processor. When we are dealing with 8 number of processor, we get a hypercube. Okay, so just have a look there. These are the interconnection that could be carried out with respect to the hypercube. Okay, so we could represent them as 1 0 0, okay, 0 1 0, so like that. Okay, the binary representation, omega. So in omega kind of interconnection, what do we observe? That was developed by the scientist Lowry as an interconnection network between the processor and memories. Okay, so here the interconnection is carried out beside processor to processor, processor to memory. Okay, so here we find certain different sorts of connections. Okay, with respect to the processor, if we observe this kind of diagram, that is nothing but a straight through connection. So this is a crisscross connection, this is upper broadcast connection, this is a lower broadcast connection. So each kind of connection is having again its own importance. Okay, so if when we are dealing with the upper broadcast, sending the data, lower broadcast receiving the data, so crisscross both receiving and sending the data through the processor, like that. Okay, so this is a simple representation of a omega interconnection. Next, pyramid, as we discussed. So here the processors at each level are being connected in such a way that the resultant interconnection network resembles like a pyramid. At level 0 we are having one kind of processor that are being connected. At level 1 another number of processor that are connected. At level 2 we are having only one processor. Okay, so this is the root processor that is connected to other number of processor. If we are going to make a clear cut view, what do we observe? This represents a pyramid interconnection. So here a two dimensional pyramid interconnection that is represented with 4 to the power d plus 1 minus 1 by 3 number of processor. So d plus 1 that indicates the number of levels. Okay, so here we are having level 0, level 1, level 2. Okay, so as the number of levels increases, the number of processor in that level are going to decrease. So that is how that is mentioned there. There are 4 to the power d minus 2 processor at level d. Okay, d minus 1 processor at level d minus 1. Okay, so that depending on okay the level, the number of processor are going to be reduced. At the same time, when we connect these processor, the analogy looks like say pyramid. So that's why we call such kind of representation as pyramid interconnection. Okay, so this is a star interconnection. So if we observe a star interconnection network of processor has property for any integer n, each processor correspond to a distinct permutation of n symbols. That is each processor we are representing with 1 2 3 and so on up to n. This indicates that the network contains p equal to n factorial number of processors. So suppose there are that means P equal to 4, the number of processor equal to 4. So how many interconnections we could expect in this kind of star interconnection means 4 factorial, okay. 3, that means number of interconnection 3 factorial, like that, okay. So this is the representation. Next, binary tree. So here what do we observe in binary tree? A root processor is kept at the top level, followed by other processor that are kept at the lower level. If you are going to observe this, it resembles a binary scenarios. That's why we call this kind of interconnection as binary interconnection. So butterfly interconnection. So as we observe in the butterfly interconnection, the processors consist of n plus 1 into 2 power n processors, okay, that are divided into n plus 1 rows. So these number of processors are divided into n plus 1 rows, okay, each containing P equal to 2 power n processor. Suppose if you are going to have a look here, so this kind of representation. So here how many rows we are going to observe? There are 4 rows, okay. So there are 4 rows here, n plus 1, that is nothing but n plus 1 rows. So here how many processors, that depends on the number of rows, okay. So the entire scenario gives a butterfly look, okay. So that's why we could call that one as a butterfly interconnection network, okay. So this is a butterfly interconnection network. So these are the various sorts of network that we observe. Next concept is decomposition, okay. Decomposition technique is very important. So why we need the concept of decomposition? So as we have discussed, the parallel algorithm concept is going to be carried out by the division of the given problem. When we divide something, what happens? That undergoes decomposition, okay. So here, to solve a problem in parallel, it is necessary to split the computations to be performed as a set of tasks for congruent execution defined by the task dependency graph. So these are the various kinds of decomposition techniques. What are they? Recursive decomposition, data decomposition, exploratory decomposition, speculative decomposition, and hybrid decomposition, okay. So let's start with the recursive kind of decomposition. So when we talk about the that means decomposition tasks, the first step is to develop a parallel algorithm to decompose the problem into tasks, okay. And each task is assigned to a particular processor, and how they are being related, okay, how the communication is going to be carried out. So that we could carry out discuss with the help of the task dependency graph, okay. Recursive decomposition. So recursive decomposition we can also call that it is going to follow the divide and conquer strategy. First, dividing it into a set of independent subprograms. Each of these subprograms is solved recursively by applying similar divisions into smaller subproblems, okay. So first of all, a problem is given to us, we are dividing that problem and following a particular strategy in each subproblem, okay, in order to achieve the result, okay. So for example, consider a quick sort. So what are the steps that are being carried out in a quick sort? Suppose we are considering an array that consists of n elements. We are selecting a pivot element in that one. Partition the algorithm into two subsequence A0, A1. Again what we are doing, again in A0 we are going to find the pivot element. We are dividing that that one into two more arrows, where one group of elements are having less the value of the pivot element, another group of elements are having greater the value of the pivot element. So like that we perform the quick sort. So let's make the concept very clear with the example. So just have a look here. So these are the set of elements which are given, okay. So 5, 12, 11, 1, 10, 6, 8, 3, 7, 4, 9, 2. So the pivot element that is we are selecting is nothing but here is 5. So we are dividing the entire given set of elements into two parts, okay. In one part we are going to find the elements which are less than the 5, and another part we are going to find the elements which are greater than 5. So this is with the given array A, we have generated two more arrays, A0 and A1. So again we are performing the division of the first subtask into another subtask. What is that one? Here we are selected one more pivot element 3. So, on the left side of that one we get a group of elements which are having a value less than 3, and right side we are getting a value that is having more than that means which are greater than or equal to the pivot element. So, like that here if 2 is the pivot element, okay, the elements that are being less than 2, 1 greater than or equal to 2, that is 2, okay, the same procedure. So, that means what here the given problem is divided into certain sub problems and same sort of technique is applied, okay. So, what technique that we are applied in the first step, that means we are finding a pivot element and we are dividing that one into two groups. One group should consist of the elements less than the pivot element, another greater than the pivot element. The same strategy is going to be followed until we are going to get the result, okay. Okay, so this is how the concept of the recursive decomposition is being carried out, okay. So, finding the one more example we could carry out. So, finding a minimum number in a given array, okay. So, what do we do? Generally we divide the array into two types or two divisions, okay. So, consider this is the group of elements that are given 4, 9, 1, 7, 8, 11, 2, 12, okay. We are going to find the minimum. We are starting from here. For suppose we are considering dividing the entire scenario into group of 2 numbers, okay. Minimum of 4, 9 and minimum of 1, 7. What is the minimum of 4, 9? That is 4. What is the minimum of 1, 7? That is 1. Again we are going to find the minimum, okay, of 4, 1. What is that one? 1. If we consider another partition, minimum of 8, 11, that is nothing but the 8. Minimum of 2, 12, that is nothing but the 2. Again the minimum of 8, 2, that is nothing but the 2. So, what is the minimum of 1, 2? That is nothing but the 1. So, for a given array, what we have done, we have came up to find out an element that is having smallest element 1. So, what was the approach that we are following? We have divided the given group of elements, and what kind of conquer strategy we have applied? Minimum, okay. For every pair of elements we were finding the minimum. The same is being carried out at every level. So, at last we are going to get the result. So, this is nothing but a recursive decomposition, okay. So, this is the algorithm that is resembled recursive decomposition. So, we are going to have an array and the number of elements with respect to the array, and this is the logic for that. Next, data decomposition. So, in data decomposition what happens? We are dividing the data, identify the data on which the computation is going to be performed, partition this data and define certain task with respect to the data, okay. This partition indicates the decomposition of the problem. So, we are given certain data, we are going to divide that data, okay, and each data is concerned with certain sort of task to be performed, okay. So, let us explain this one with an example. So, data decomposition we can talk about 3 different approaches: output data decomposition, input data decomposition, intermediate data decomposition. That means what? Output data decomposition, with respect to the output that we are getting, there we can perform the decomposition. At the time of input itself we can perform the decomposition. So, either during the process we could perform the decomposition, that is the intermediate data partitioning, okay. Next, data decomposition, let us discuss the first one, output data decomposition. So, here what happens? Often each element of the output can be computed independently. So, let us make the concept very clear with an example. So, consider matrix multiplication. So, what do we observe? When we multiply two matrices with respect to, okay, row of one and column of another matrix, we get another group of elements C11, C12, like that. What does that C11 represent? Okay, the multiplication, okay, A11 B11 plus A12 with respect to B21, like that, okay. So, again we are getting four more results, that means here what do we observe? To get C11, that resembles one task, okay. C12, that is another task. So, here if we are going to follow this one sequential, what happens? This takes a bit of time. So, we know what to do in task 1, what to do in task 2, 3 and 4. Due to that, what happens? The tasks are divided clearly and we could get the approach. So, these are the 4 tasks that could be performed okay, parallelly now to get the result of C11, C12, C21, C22, okay. So, this is the resultant. The same task could be performed in another scenario also, okay. So, this is another sort of decomposition, okay. The same matrix multiplication could be carried out in two sort of divisions, okay, this one and this, okay, both are right. Next, see output data decomposition, an example. So here what do we observe? We are given a database, that means here we are given certain database transactions, and we are having certain the frequencies of the terms that we are getting there, okay. So consider a problem of counting the instances of given item sets in a database of transactions, okay. So this is a database transaction. So if we observe, okay, these are the number of transactions that are being carried out. What kind of transaction? Here we are performing transaction input item sets. So here this is a database transaction, these are the item sets and the frequency of them. That means what? This is the database transaction that is carried out, okay, A, B, C, E, G, H, like that. So here item set, so that means in this all kinds of transaction, how many kinds we got this item A, B, C. So that is the frequency, only one time, D, E, that is 3 times, okay. Next, we could carry out another example in the same scenario, partitioning the frequencies and themselves among the tasks, okay. So here these set of item sets are being classified into two types, two partitions, okay. First first 4 we have considered here, another 4 we have considered here. Again we are finding the same thing, okay, the frequency of them. So this is how we, rather than making it in the simple task, we have divided into 2 more tasks, okay. So like that, that is the approach. So this is the example that we could discuss there. Next, input data partitioning. So here what happens, in the input itself we are going to carry out the partitioning. That means if we observe in the previous thing, these are the input, that means database transactions that are carried out. We are dividing the database transaction at the input itself, okay. So if we observe here, so we have considered only one part of the input, another part we are mentioning here, we are dividing that one into 2 number of tasks, okay. So like that, in order to get the results parallelly. So we could further divide that this one, okay, input and output. At input also we are dividing, at output also we are dividing. We are taking some sort of database transaction at one set, another set we are taking another, okay. So like that we could divide this entire complex task into 4 different scenarios, task, and then carry out the thing, so that we could get the results in a faster way, okay. So this is also the same example of the matrix multiplication, okay. So next, exploratory decomposition, that is used to decompose the problem whose underlying computation correspond to a such space for the solution. That means what, we are going to carry out the decomposition here, such that for every next task we need certain sort of space in order to solve that one. Consider a 15 puzzle problem. So what is that 15 puzzle problem? The diagram makes it very clear. So this is a set of numbers that are being given. This is a 15 puzzle problem. So here one free space is there, and we have to arrange the elements in a proper order. So for each position of the free space we are having 4 different moves, okay. Let's make it clear. Suppose here there is a free space. So this is the initial and this is the final one. How we are getting that final position there? Okay, this free space should be moved in such a way that all the elements could be arranged in a particular order. How we are going to achieve that one? Here if we observe, okay, here if we observe, there are 4 possibilities. Either we can move the free space towards right, towards left, towards upward, towards down. That means what, for every free space there are 4 different subtasks, okay. So again if we consider the subtask, again for that also there are 4 different moves, okay. So that could be clarified more clearly with this example, okay. So this is the first task 1, task 2, task 3, task 4. That means what, here the free space is moved downwards, towards upwards, towards the left side, towards the right side. Again for each task we are having 3 to 4 more different tasks that we need to perform in order to get the result. So like that we have to move. Such kind of scenario is nothing but exploratory decomposition technique. Next, speculative decomposition technique. So here what happens, when a program may take one of many possible computationally significant branches, okay, depending on the output of the other. In such kind of scenario we could go with speculative decomposition. For example, consider a switch statement. switch statement, what do we observe? There are many things in the switch statements, depending we are going to find out the correct required one. If the required one is going to match, we could carry out that particular statement. So such kind of scenarios are nothing but the example of the speculative execution. Okay, so we can speculative execution, that is nothing but one of the live example for that one. So consider today's different events that we are doing. We get up, we get ready, drive to work, okay, work, eat lunch, work for some more time and drive back, we eat the dinner and then sleep. These are the various activities. We could carry out that one in the form of the switch statements like that. Hybrid decomposition, as the name itself suggests, it is nothing but the combination of two or more decomposition techniques that we are discussing. Suppose here hybrid decomposition, it is a combination of two, suppose these are the given set of elements 3, 7, 2, 9, 11, 4, 5, 8, 7, 10, 6, 13, 1, 19, 3, 9. This is a group of elements that are given. We are set to partition them. Okay, so first of all we are going to achieve the data partition. After that we are going to find the minimum of that one. Okay, so for that one we are going to follow the recursive decomposition. So decomposition where that is a combination of two or three decomposition approaches is nothing but called as a hybrid decomposition.